All right, so let's begin. So, okay, today we are doing problem this problem set number 5, and there's a few things that I need to talk through. Actually, I also need to present probably one thing in the slides. So let me switch over to that real fast. So right in the slides we have these properties about the logarithm function. And the place where this comes up is actually with problem number 4 that involves logarithmic differentiation. So you actually need to remember these. And these are actually just algebra things. So hopefully you do have some recollection of them. So basically, what this is saying is that if you have a product inside the logarithm function that will split and turn into addition outside, if you have a division inside the logarithm, you can turn that into subtraction. And if you have exponentiation inside the logarithm function, that can turn into multiplication outside. You can just pull that exponent out. And then we have the fact that logarithm and exponential functions are inverse functions to one another. So if you put one around the other, like this ln of an exponential, that's just the original function. That's just x. The two will cancel. And same if you go the other way around. If you wrap an exponential function around a logarithm function, that will also cancel. So these are just nice properties to know about for the logarithm function. And I think that's really all that I wanted to say from here. The rest I need to just sort of write out. Yeah. Yeah. Actually, this says something about, yeah, you're allowed to use notes and stuff. Very different from typical class. Okay. All right. I don't need to share my full screen anymore. I can switch over. All right. So, right, with those algebra rules, let's now start talking about some of the calculus rules. So the first thing that you need to know is the derivative of just the natural log and the derivative of the exponential. So the derivative of the natural log is 1 over x. And the derivative of the exponential function, e to the x, is going to be, oh no. Let's try to scroll a bit. Derivative of the exponential function is just the exponential function itself. Okay, so these are sort of the easiest versions of these rules. Then we have to complicate matters a little bit because we are actually allowed to work over an arbitrary base. So this ln function, this natural log function, is actually a logarithm over the base e. Okay, and when you normally write log, this actually is a log base 10 typically. But here we're just going to say over an arbitrary base b. And what is the derivative rule in this case? Well, I'm going to say that it's ln of b times 1 over x. You treat this 1 over ln of b. This is sort of a correction factor. It's just a number, and you're just sort of scaling the original answer. And for this exponential function, well, say you're over a different base. Instead of e, you're over the base a. You're taking the derivative of this exponential function. What is this going to be? Well, I'm going to say it's ln of a times a to the x. So again, you have a correction factor that comes into play. And notice like what's nice here, like these two rules on the bottom are actually generalizations of the rules on the top. What happens is if you just remember the fact that ln of e is equal to 1, you see that for the special base of e, these bottom rules will restrict into these rules on top. So these rules on the bottom are generalizations. There's one additional thing I can say about this, which is that you can actually see this rule a little bit more easily if you know about something called the base change formula. So there's a property of logs where what it says is that you can just rewrite any logarithm over as being two other logarithms, but over like an arbitrary base. So usually what you'll see is like this, you can write it as log base c of x over log base c of b, right? You can change this log base b into a log base c. What's helpful though is actually if you don't just use c other arbitrary thing, but we use a useful log that we know how to compute things with. And so in this case, if we just use the ln version, like log base e, ln, notice that what we get, well, ln of b is just a number, so we will get this guy, and then ln of x is just this 1 over x. So you can very easily see that this is going to give you that when you take its derivative. That's a very easy way to argue this statement. I don't think this one is so easy to argue though. Well, actually, now that I think about it, I probably can argue it, but I have to play with it a little bit. I won't do that. Okay, so yeah, so this is exponential and log derivatives. Another thing that we need to say are inverse trig functions. So arc trig, g trig derivatives. And so these inverse trig functions, the rules will also split up in a way similar to the trig derivatives. So sine inverse is going to be 1 over the square root of 1 minus x squared. Normally, we would have you memorize some of these. Cosine is just negative 1 minus x squared. Tangent inverse looks a bit different. 1 over, I normally write this as x squared plus 1. Although some people like to write it as 1 plus x squared, but that's how I normally write it. Cotangent has a negative in front. And then secant and cosecant are just the really weird ones. 1 over absolute value of x, square root of x squared minus 1. And then cosecant 1 over x squared minus 1, and with a negative in front. So just like with the trig derivatives, you see that these inverse trig derivatives split up into families, and the co-functions have the negative in front. And so you can basically just remember this table if you remember what the derivative inverse sine, inverse tangent, and inverse secant give you. A little bit tricky to do that, but it's possible. And in a typical semester, we would ask that you remember inverse sine and inverse tangent. We usually don't test you on these, but then when you go for far enough in math or calculus or whatever, at some point you're expected to know these, and also to know like hyperbolic stuff as well, which I don't know, but okay. And I think that's everything that you, well, apart from logarithmic differentiation, but we'll talk about that when we get to number 4. So yeah, so those are the rules. Good, it's a good idea to get familiar with them. And now we're just going to start using these rules to calculate these derivatives. Okay, so right. Notice here, this is an exponential function with an inner function of 5x. So there is actually a chain rule for this first guy. So when we take the derivative of e to the 5x, well, the rule for exponential functions says the derivative is just going to be the original guy. But then we have a chain rule, which says you have to multiply by the derivative of the inner function. Derivative of the inner function is going to be 5 because it's derivative of 5x. So we have this. And if you thought ahead, you would have just rewritten this. In fact, I really want to emphasize you really should just think ahead for that kind of. If it's just a number, it makes more sense to put it in front. So I will rewrite it like that. 7x, that's the special case of a general exponential function. Okay, and so we have that there is an ln of 7 that pops out in front. So we write ln of 7. And I typically put parentheses around this just to sort of help remind myself that this is just some number. Okay, it's just some coefficient in front that scales this 7 to the x function. Okay, and now this guy is the hardest bit for this, arctan of this. So what you have to recognize is for the arctan function, which is right here, you have to square the inner function, right? You have the function, if inside the arctan you have just x, then you end up squaring x. But here we have some complicated function. We end up needing to square that function, and then you have to proceed with chain rule because, well, it's a complicated inner function. You have to use chain rule to take its derivative. And so what we will get is 1 plus and then 3x to the 7 plus 4x all squared. And then I could put the chain rule off to the side, but since this is just a number here, I may as well just put it on top. Okay, and now I just write the derivative. So this is going to be 21x to the 6 plus 4. Okay. Right, and that's it for part A. For part B, you can see right away that this is a product rule, right? So, and also this e to the x, its derivative is really easy. So we're gonna just go ahead and think of product rule. First, we take the derivative e to the x, which is just, or e to the t, which is just e to the t. And we copy the other guy down. And then we say plus. And then the next thing is we copy down the first guy, and then we take the derivative of the second guy. So I need to take the derivative inverse sine of t cubed. So you have to remember, according to this, derivative of inverse sine is that. We have to still square the inner function. 1 over the square root of 1 minus, and then so normally we have to square this. That's going to become a t to the 6. Okay, and then we can multiply this by well, we have to do chain rule because it's not just inverse sine of x or of t, but it's of t cubed. So we have to take the derivative of this t cubed function. That's going to give me a 3t squared. And so we have that as the final answer. For C, before I do anything, I would notice this ln of w squared. This simplifies just a little bit, and this simplification helps because it allows us to avoid a chain rule that would pop up otherwise. So I know like my log properties, so I know that I can pull that exponent of 2 outside and it becomes just a scalar multiplication by 2. All right, so now we just proceed and we do quotient rule. Okay, and just as a quick reminder, if you still are not comfortable, well, actually, I'm sort of being very redundant if I do that, so I'm going to write it like this. So yeah, you should know quotient rule by now, but I'm just going to write it just in case. Du prime minus ud prime over d squared. Okay, so this is going to be, I copy the denominator, tangent w, and then I have to take the derivative of this numerator. Okay, so I'm thinking of the derivative of this 2 ln w. So that's just going to be 2 over w. And then plus, now we have a logarithm over a different base. So that means that we have a scale factor that pops out, which is ln of the base, ln of 2, times, and then how would we normally take the derivative of the log function? Well, we reciprocate the contents inside the log function. So it's just going to be this. This is the first half of quotient rule. Then I have to do minus numerator times derivative of denominator. So we're going to copy the numerator straight, just as is, log 2w, and multiply by derivative of denominator, derivative of tangent. You hopefully just remember it's secant squared. And then this is all over denominator squared. So we have a tangent squared w on the bottom. Okay. Any questions so far? No? Okay. For D, what I want to do is I want to treat a slightly simpler problem instead. This is actually a very typical thing that you can do. Just nest a whole bunch of ln's inside of each other. But so before we deal with the case of multiple ln's, why don't we just deal with ln of x, and you'll see what we do. So notice that this is a chain rule, right? You have a function inside of another function, and chain rule says that you take the derivative of the outer function first. Derivative of the ln function is 1 over x, as you know, but I want you to think of this as the idea of reciprocating. Okay, so whatever's inside the ln function, you reciprocate it, and then you tack on a chain rule. So because notice normally this would be 1 over x, but because our inner function is ln of x, we actually have 1 over ln of x. Okay, and so this is the derivative of the outermost function, derivative of this ln outside. Then we have to tack on a chain rule, which says we take the derivative of the inner function, which in this case is ln of x. That's going to give me 1 over x. And that's where the chain rule terminates. And so this is my final answer for this problem. And so now you see that if you have 3 ln's nested, it's going to work similarly. So we take the derivative of the outermost ln function, get 1 over ln of x. Then we have a chain rule, which says take the derivative of this ln of x. And so that's going to take the derivative of the outer function, the ln, and it's going to reciprocate the inner guy. You get that. And then you just tack on another chain rule there. So this ends up being the full answer for part D. Are there questions on that? So it's pretty wordy, but hopefully you kind of understand how the process works. All right. Not seeing any questions, so we'll just keep going. Number 2 is actually really simple. So converting all the words, the problem is actually asking us to calculate h prime of 5, right? And notice that h is this function. It's actually a pretty simple function to take the derivative of. So first we take its derivative. So we have ln of t plus 1. Well, just like before, taking the derivative of the ln function is just going to reciprocate the contents inside of it. So you have t plus 1, and then, well, you would have a chain rule, except t plus 1's derivative is just the function 1. So we don't need to write anything for that. And then you just plug in 5. So you get 3,500 over 6, which is okay, so I got 1750 over 3, which is 583.33 feet per minute. So since this problem is in terms of feet per minute, like since it gives you units, you should remember to put units. And I can go ahead and box this. Right. So number 2 is pretty straightforward, I would say. Number 3 is also pretty easy. At least part A is pretty easy, I think. So, well, n of 0 and n of 4 is just asking you to plug in. Interpreting might be a little bit more thinking. So, but n of 0, just plug into that, and because the numbers are pretty messy, you kind of should just use a calculator to do it. The only thing you could do is n of 0, actually, because you know that the exponent is going to turn to 0, and e to the 0 is 1. But n of 4, I don't expect anyone to do that by well, you can't really, can you? Because this exponential is going to be a decimal. You get 0.723. Okay. And now for interpreting. So the important thing to note here is the units, right? So the number of cases is measured in terms of thousands, and well, you're going to want to use pretty much all the words that are used in the word problem. So the idea is if we're going to convert this mathematical statement into words, what does it actually say? Well, it's going to say that there are 5,300 cases of influenza in New York City in 1960. And then for this one, this statement is actually that there are 723 cases of influenza in New York City in 1964. Okay, so that part's fine. For part B, it wants us to calculate n prime evaluated at things. So first thing we need to do is actually calculate what the n prime function actually is. So we have to take the derivative. Okay, well, so notice this is an exponential function, which means that you would just copy down the original guy and then you tack on a chain rule. So we copy down the original function, 0.093 t squared minus 0.87t, and then we have a chain rule. So we had to take the derivative of this inner function, which is just a polynomial, so it's not too bad. And what would we get? 0.186t minus 0.87. Okay. And well, you just have to plug into this function. So certainly have to use a calculator, I think. For this one, for n prime of 0, you can get negative 4.611. For n prime of 4, you'll get negative 0.0911. You should always make sure that you actually do get these values. Like, make sure you can type things into a calculator correctly. Right. And right, so converting these into words now. Well, n prime is denoting a rate of change, right? So we want to view these things as rates of change, and we're still talking about like cases in terms of thousands. So we're going to have to multiply by 1,000 to straighten things out. Since it's negative, this is saying that the rate of cases is decreasing, and just massage it to get a phrase that makes sense in English. So what I wrote is that the number of influenza cases in New York City in 1960 is decreasing at a rate of 4,611 cases per year. And then for this one, it's pretty much the same thing. I'm going to abbreviate this, just say number of cases in New York City in 1964 is decreasing at a rate of, and then the only thing that changes is this becomes 91. Yeah, 91. And this is still cases per year. Okay. So when you actually write it on paper, you probably just rewrite the same thing. Otherwise, I think that's nothing much to add to this. And so now we get to number 4, right? So logarithmic differentiation. So this is kind of a specialized technique in a way. It's a bit of a weird thing. I guess the real natural way that this comes about is by considering if you're just given this function and you're asked to take its derivative, like you kind of get immediately stuck. Okay, because the two rules that you know of so far, let me put this above. The two rules that you know of so far are if you just have a variable in the exponent or if you have a variable in the base. If you have either x in the base or x in the exponent, you know how to deal with them. This is using the exponential rule that we have just learned, and this one would be the power rule that you learned a long time ago. But here we actually have a combination of the two. We have x both in the base and in the exponent, and that doesn't match either of these two rules. In these two rules, you expect one of the things to be fixed, but here we have both things vary. with respect to x. And so this is where this is one instance where we are forced to use this technique of logarithmic differentiation. So let's talk about how that works with this easy case before we work on the homework problem. So the way that this works, the idea is that when you take the logarithm of this function, you're going to make that exponent pop out off to the side, and it's going to turn it into a product rule, and you can handle a product rule. Okay, so the normal way that I do this is I call the functions a name, I call it y, and then I take the logarithm of this whole equation. So if I gave myself a bit more space, I would just put an arrow with this ln, denoting that I'm taking the logarithm of both sides of this equation. And so this is going to turn into x ln of x. And then the next thing is now I can take the derivative. And I need to be a little bit precise about this. So I'm taking a derivative with respect to x, because the right-hand side is going to do something a little unexpected, okay? The right-hand side is going to be 1 over y times y prime. This extra y prime is something that you'll find out about eventually, probably right after the exam. Where this is a section called implicit differentiation. So what's happening is you'll learn about this a bit later. It's a bit out of order the way that we're covering it this time around, but what's happening is this y is a function of x. You can kind of see it here. So you kind of imagine this y is actually a function of x. So you have ln of y of x. And so when you take the derivative of this guy, taking the derivative of ln is going to give you 1 over y, but then y is also a function of x, sort of. And so you have a y prime that occurs. That's why you've got this extra chain rule piece hanging about. Okay, and then lastly, well, you're taking the derivative of this whole equation. We took the derivative of the left-hand side. Now you just do the right-hand side, which is a product rule. So you get ln of x plus x over x. And then finally, to answer the original question, we were trying to take the derivative of this function y. Well, we have y prime here. So if we solve for y prime, which is dy dx, if we solve for y prime, we will get the answer that we were looking for. And so all we have to do is just multiply both sides by y, and y is x to the x. So multiplying both sides, we just have to copy the right-hand side, and there we go. So then we would end up boxing this guy as our final answer. And that's pretty much the whole process for logarithmic differentiation. First, we take a logarithm, which simplifies our situation so that we can follow it up by taking a derivative. Okay, and then after we take that derivative, we will have this 1 over y that we need to move to the other side. So then we multiply both sides by the y, and we also have to remember to replace out the y with what it's defined as being. And so this is the steps for logarithmic differentiation. And part A is motivated by this kind of principle. If you have a function of x in the base, a function of x in the exponent, you have to use logarithmic differentiation to deal with it. Right? You see that in part A. But part B is slightly different. And I'll just talk about that before we do it. So part B is using a different principle for why we might want to use logarithmic differentiation, which is that it will simplify our calculations a lot. Okay, notice here we have, if we were to do this without logarithmic differentiation, which we totally can do, it would involve a quotient rule, a product rule, a bunch of power rule. Well, maybe not a bunch, but it will also involve power rule. So it'll become some pretty heavy, really long thing to write. But if we take a logarithm of this, it will drastically simplify what we need to then take the derivative of, because the logarithm is going to turn the division into subtraction, turn the multiplication into addition, and pull those exponents down. So it basically gets rid of the power rule that we would otherwise have to do. So it simplifies what kinds of rules we're going to be using, and it's going to simplify like the way that our answer is written. simplify it a little bit. It's still kind of nasty, but it's not as bad. Okay, right. So those are the two ways that we normally see this method show up. All right, so let's go ahead and now try doing this. So first of all, for this, I would start by giving this function a name. So let's call x to the 2 sine of x, call it y, and then we take the logarithm of this equation. And so this is going to become 2 sine x ln of x. Okay, and then next we take the derivative. And so, as I said before, this guy turns into 1 over y times y prime. This side is just a product rule, so hopefully you can do that. Cosine x ln x plus 2 sine x over x. And then lastly, we need to move this 1 over y to the other side. Y prime is equal to, and then what is y again? It's this x to the 2 sine x. And then we just copy down what we previously computed. And so there we go. Yeah, so that is the answer for A. And now for 4B. Well, here it actually has given us a name for the function, so we can just use that name. And what I'll do is I'll write this as ln of f of x. Okay, and then we need to wrap logarithm around this whole function and then just sort of pass it through all of those operations. So if you're comfortable enough with logarithms, you should be able to do this in one pass. You don't need to like write a whole bunch of different algebraic steps that change it from one thing to the next. If you need practice, then I would say that there should be some practice in this textbook that I've mentioned to you guys in the past. So, right. We're taking the logarithm of that. It's going to turn multiplication into addition. It's going to turn the division into subtraction. The exponents are going to pop down. And then the other thing is ln of this e to the 3x squared. Remember that ln and exponentiation are inverse functions to one another. So what that's going to do is it's going to cancel out both of that, and you're just going to be left with the 3x squared. So we'll start off with that 3x squared, and then we'll have a plus 7 ln of 92x plus 3, and then minus 3 ln of 9x to the 6 plus 5x squared. Okay, so that's what you get when you apply log to that and then just run it through everything. Okay, now we take the derivative. All right, so right, the way that this is written, we know that we would do 1 over f of x, and then we multiply by f prime of x. Okay, and we're solving for f prime of x. That's what we want to find. So we will have to multiply by f of x to both sides later on. Okay, we take the derivative of the right-hand side now. So this is just a 6x. This is going to be a 7 over 92x plus 3. And then chain rule is going to say take the derivative of the inner function. So derivative of this, well, it's a line, but it's a polynomial. You get times 92. And then for the last term, 3 divided by 9x to the 6th plus 5x squared. And then we have to do a chain rule. So we take the derivative. I can just put that on top. And that's going to be a 54. Yeah, 54 x to the 5 plus 10x. Okay. Lastly, we solve for f prime of x. Okay, so this is where we just don't have to think much, just need to copy things down. So f is the function that was given to you. 92x plus 3 to the 7 all over 9x to 6 squared to the third. Okay. And then all of that is being multiplied against these three terms here. So you just copy those three terms. Don't need to do any multiplying or simplifying. You can't really even simplify for this problem. So I could just copy paste, but if you're writing this on paper, you have to write it out. So, okay. And so there you have it. That's the last problem. All right, well, are there any questions on this problem set or any of the previous work? So we have
I'll have questions next week.
Next
Or
week?
not next week.
Next time. Yeah.
Next time.
Yeah. Okay. Sure. I mean, if anyone has questions right now, like we can talk through things. 1D. Yeah, sure. Let's see. What is 1D? Yeah. Yeah. So my recordings are on YouTube. A lot of people keep asking me this. I don't know why. Sent it out like second email I sent you guys. Yeah. Okay, so well, there are 10 additional minutes. If you have anything you want to ask, we can go through some additional stuff. Otherwise, we could end it here. It's up to you guys. No questions. All right. I guess I'll stop recording.